You're now going to review two more AWS services that you can use with containers. These services are AWS Fargate and Amazon Elastic Kubernetes Service, or Amazon EKS. You're also going to learn about AWS step functions. AWS Fargate is defined as a compute engine for Amazon ECS and Amazon EKS, and as such, it can be used with ECS to run containers without the overhead of needing to manage any servers or clusters. In this way, ECS can use containers that are provisioned by Fargate to automatically scale, load balance, and manage the scheduling of your containers for availability. Fargate provides an easier way to build and operate containerized applications by removing the need to choose server types, decide when to scale your clusters, or optimize cluster packaging. You can run both Fargate and ECS tasks in the same cluster. Fargate capabilities are available natively in ECS, so you don't need to learn new API actions to run containers on Fargate. Fargate is available with 50 different combinations of CPU and memory to match the needs of your application. You can use between 2 GB and 8 GB per vCPU to enable various configurations. So you can best match workload requirements, whether they are general purpose or compute or memory optimized. You pay based on the task size, and you also pay only for the time resources that are consumed by the task. In terms of granularity, the price for CPU and memory is charged on a per second basis, but be aware there is a 1-minute minimum charge. You will now learn about the components of the Fargate and Amazon ECS stacks in a sample deployment. First, you create a task definition that defines how ECS handles scheduling and orchestration. Fargate manages the placement engine, the cluster, and also the infrastructure. The resources that are managed by Fargate include agents, AMIs, and other resources related to the Fargate service. To help you visualize this, consider what happens when a new version of Docker is released. If you don't use Fargate, you must think about an upgrade strategy and then manually upgrade the version of Docker on each node in the cluster. This process would require draining that node, scheduled downtime, and so on. With Fargate, all these tasks are taken care of on your behalf. Amazon ECS has two modes. You have the EC2 launch type and the Fargate launch type. With the Fargate launch type, all you need to do is package your application in containers, tell it what the CPU and memory requirements are, define your networking and IAM policies, and then launch the application. Fargate manages all the scaling and infrastructure that are needed to run the containers in a highly available manner. Running containers as Fargate or as EC2 is a launch time decision. You don't need to add any additional plugins to run containers as Fargate. In summary, with Fargate, you no longer need to provision, configure, or scale clusters of virtual machines to run containers. If you want to get a service or application up and running quickly, Fargate is a good way to make it happen. That is, you write your task definition, choose Fargate, and your application is up and running. Here's another use case. Say that you must quickly migrate a monolithic application to the cloud. By containerizing the application and then launching it with Fargate, you can concern yourself less with the cluster and instead focus on the application itself. Another use case for Fargate is when your service or application is highly variable but unpredictable in the resources it might use over time. Fargate can add additional infrastructure capacity automatically, according to whatever bounds you set. So you don't need to worry about your service running out of resources and becoming unavailable, and you don't need to over-provision resources for the highest possible demand and end up paying for resources that you don't need. With this in mind, why might you still want to consider using EC2 mode? You might choose to use EC2 mode for your Amazon ECS tasks if you are a heavy user of EC2 spot instances, or if you paid for reserved instances. Fargate manages all the infrastructure on your behalf. Because it's charged by the CPU and memory second that's consumed, there is no way today to apply these features across spot instances or reserved instances. If the services and applications are based on Microsoft Windows, EC2 mode is still probably the best option for deployment because you can use Windows AMIs and configurations in your cluster, which Fargate doesn't support currently. And finally, if you need more granular control of your EC2 instances, then EC2 mode is the clear choice. The need for granular control could come from compliance or governance requirements, or because of broader customization options. Now, you'll learn about Kubernetes. What is Kubernetes? It's open source software for container orchestration. It enables you to deploy and manage containerized applications at scale, and it uses the same tool set on-premises and in the cloud. Kubernetes works by managing a cluster of compute instances. It runs scheduling containers on the cluster based around where compute resources are available and the resource requirements of each container that will run to support your applications. Containers are run together in logical groupings called pods, and scaling up involves increasing the number of pods for an application. The Kubernetes software decides when and where to run the pods. It manages the traffic routing and scales your pods based on utilization or other metrics that you define. In terms of resourcing, Kubernetes automatically starts pods in your cluster based on their resource requirements. It will automatically restart pods if they fail or if the instances that they run on fail. Each pod is given an IP address and a single DNS name, and Kubernetes uses this to connect your services with each other and also with external traffic. The main function of Kubernetes is to enable containerized applications to run at scale across a cluster of servers. It's easy to move applications from local development machines to production deployments on the cloud using the same tooling, and this is one of the key advantages of Kubernetes because it can be used to run containerized applications anywhere without needing to change the operational tooling. Because it's an open source project, it's easy to add new functionality to Kubernetes. There's a large community of developers and companies that build extensions, integrations, and plugins that help Kubernetes users do more. In AWS, you can either manage the Kubernetes infrastructure yourself by running it on EC2 instances, or you can use an automatically provisioned, managed Kubernetes control plane with Amazon EKS. EKS makes it easy to deploy, manage, and scale managed Kubernetes control plane with Amazon EKS. EKS makes it easy to deploy, manage, and scale containerized applications. It runs the Kubernetes management infrastructure across multiple availability zones to eliminate a single point of failure. EKS is certified Kubernetes conformant, so you can use existing tooling and plugins from the AWS Partner Network, or APN, and the Kubernetes community. Applications that run on any standard Kubernetes environment are fully compatible and they can be migrated to EKS. The diagram shows how EKS works. First, you create the cluster with the parameters you need, such as the VPC and subnet IDs. Next, EKS automatically deploys Kubernetes control plane nodes. Next, you deploy worker nodes. You add the number of worker nodes that you need to your EKS cluster. Then, you connect to Amazon EKS and point your preferred Kubernetes tooling at your EKS cluster. Finally, you deploy your Kubernetes applications to your EKS cluster. Now you will learn about Amazon Elastic Container Registry, or Amazon ECR. ECR is a fully managed Docker container registry, which makes it easy for developers to store, manage, and deploy Docker container images. It's integrated with Amazon ECS, so you can store and run and manage container images for applications that you run on ECS. You can specify the ECR repository in your task definition, so ECS can retrieve the images for your applications. ECR supports Docker Registry HTTP API version 2, and this API enables you to interact with ECR by using commands through the Docker command line interface, or by using your preferred Docker tools. Thus, you can maintain your existing development workflow and access ECR from any Docker environment, whether it's in the cloud, on premises, or on your local machine. ECR stores your container images in Amazon S3, so it benefits from the high availability and durability of S3. You can use namespaces in your ECR registry to organize your repositories based on your team's existing workflow, and you can set the API actions that another user can perform on your repository. You can share your repositories with different users and AWS accounts. ECR uses IAM for access control, so you can control which EC2 instances or users can access your container images. You can take advantage of HTTPS to transfer your container images to and from ECS, and images are automatically encrypted at rest with S3 server-side encryption. And lastly, there are many third-party tools that can be used with ECR. Next, you'll learn about using AWS step functions in serverless workflows for system operations. With AWS step functions, you can coordinate multiple AWS services into serverless workflows. This means that you can build and update applications quickly. For example, you could design and run workflows that combine services like AWS Lambda and Amazon ECS into feature-rich applications. These workflows are made up of a series of steps, with the output of one step acting as the input for the next step. Step functions translates your workflow into a state machine diagram that is easy to inspect and understand, which makes it easier to explain to others and easy to change. You can monitor each step as it happens, which means that you can identify and fix problems quickly. Step functions automatically trigger and track each step. If there are errors, step functions will retry so your applications run in order and as expected. To read more about step functions and see architectural examples, search for Step Functions Use Cases in the AWS documentation. Here's an overview of how to work with step functions. First, you define the workflow. The individual tasks are then represented as a state machine. Individual states make decisions based on their input, perform actions, and then pass their output to other states. The step function console gives you a graphical representation of the state machine to visualize the application logic. States can perform different functions. For instance, they could do work like performing a task, or they could make a choice about which branch in the workflow to continue on. It's possible to configure tasks to invoke code that is hosted in a Lambda function, a container, or an instance. The code can then be run as many times as needed for a period as long as 1 year. And as workflows evolve, you can change the tasks, change the step order, add tasks, or delete tasks, all without needing to make any code modifications. And that's it for now. Thanks for watching, and see you in the next video. You'll now review containers and one of the AWS services that you can use with containers, Amazon Elastic Container Service, or Amazon ECS. Like virtual machines virtualize hardware, containers are used to virtualize an operating system. Amazon EC2 runs virtual machines, where an entire operating system like Linux or Microsoft Windows has been virtualized. Containers, on the other hand, are smaller, and they don't contain an entire operating system. Instead, containers share a virtualized operating system and run as a resource-isolated process. One of the greatest benefits of this is ensuring quick, reliable, and consistent deployments. Containers literally hold everything that the software needs to run, which includes libraries, system tools, code, and also the runtime. Containers deliver environmental consistency because the application's code, its configurations, and its dependencies are packaged into a single object. Containers are the building block that you can deploy on any compute resource regardless of software, operating system, or even hardware configuration. Containers also provide process isolation. There are no shared dependencies or incompatibilities because each container is isolated from the others. Whatever you package as a container locally, such as on a developer's laptop, will deploy and run the same way, whether in testing or production. And process isolation provides operational efficiency. Another advantage is that you can run multiple application components running on the same EC2 compute instance, which is referred to in the context of containers as a container instance. You will often encounter the term container instances in the context of Amazon ECS, but it's important to remember it refers to the whole EC2 compute instance instead of any individual container. You can also specify the exact amount of memory, disk space, and CPU to be used by a container on an instance for both allocating and constraining resources. Containers boot quickly, and the reduced footprint enables you to quickly create and terminate applications or tasks. Note that a task definition can include one or more containers. This means you can rapidly scale applications up or down. Containers also increase developer productivity because they remove cross-service dependencies and conflicts. Each application component can be broken into different containers that run a different microservice. Also, containers are isolated from each other, so you don't have to worry about synchronizing libraries or dependencies for each service. This means developers can independently upgrade each service because there are no library conflicts. Finally, you can track versions and dependencies of your applications with a container manifest, and you can inspect differences between versions and roll back to previous versions. Now we will discuss Docker. Docker is a software platform that packages software, such as applications, into units that are referred to as containers. With Docker, you can quickly build and test and deploy applications. The containers hold everything that the software needs to run. Docker, then, is installed on each server that hosts containers, and it provides simple commands that you use to build, start, or stop containers. By using Docker, you can quickly deploy and scale applications into any environment. What are the most appropriate use cases for Docker? Docker is best used as a solution when you want to standardize environments, reduce conflicts between language stacks and versions, use containers as a service, run microservices by using standardized code deployments, or when you need portability for data processing. Now look at the graphic on the left. You can see that a single host operating system has Docker installed on it. It also has 3 applications that run in 3 separate containers. Each container relies on the virtualized OS provided by Docker. But each container also has its own isolated binaries and software dependency libraries. In the graphic on the right, 4 applications are hosted across 3 guest operating systems. Each guest OS could be an EC2 instance, for example. Applications A and B are hosted on a single guest OS. Application C is hosted on a separate guest OS. Application D runs in a non-container environment on a virtual machine. And as you can see, it does not use Docker. Another key point is that you can have a single application that spans multiple containers, although you don't see this in the graphic. Also note that it's common for deployments to have multiple containers run on a single installation of Docker, like guest OS number 1 with applications A and B. Although containers have many advantages, they also come with a few challenges that you must be aware of. First, because the number of containers can grow quickly, you might run into container sprawl. This tends to happen when the number of containers grows significantly and container distribution is not being managed properly. Also, the rapid growth in the number of containers can complicate tracking the version differences of a container. AWS can help with these challenges in a couple of ways. First, Amazon ECS enables you to control the placement of tasks across different EC2 container instances. And you can also use clusters and targeted launches to enable version control and specific task ownership. You can also use an Amazon Elastic Container Registry or Amazon ECR repository in your task definitions to attach the necessary role to your EC2 container instances. This is called Amazon EC2 Container Service for EC2 role, and it allows the EC2 instance to retrieve the appropriate images for the application that is being managed by the ECR repository. Before moving on, here's some additional terminology and some additional challenges with containers that you should be aware of. First, the phrase bin packing means that there is limited space available in the host where the containers can run. You must decide the best placement of each container to maximize application performance. You might also run containers that are no longer needed, which are sometimes referred to as zombie containers. A zombie container is a Docker container that refuses to stop when it's issued a command. Normal containers shut down gracefully when you issue a stop command from the AWS Management Console or an API. Zombie containers refuse to stop because they can't process the init command to stop gracefully. In Amazon ECS, you can use the init process enabled flag, which runs an init process as PID1 in the container. This enables a graceful exit of all containers. It also reduces the zombie container issue. Finally, you might experience the issue of having containers that you need but are no longer running. These kinds of containers are known as disappearing containers. Next, you'll learn some more details about the first AWS service that you could use with containers, or Amazon Elastic Container Service. Amazon ECS is a highly scalable, high-performance container management service that supports Docker containers. Here's some more details about the benefits of Amazon ECS. First, as already mentioned, ECS is a highly scalable, high-performance container management service that supports Docker containers. It also enables you to run applications on a managed cluster of EC2 instances. It also provides flexible scheduling. ECS has a built-in scheduler, or you can use a third-party scheduler like Apache Mesos. And you have the option of performing task, service, or daemon scheduling. The ECS APIs make it straightforward to integrate third-party solutions like other schedulers or pipelines to support your software delivery process. ECS launches your containers in your own VPC, which allows you to use your security groups and network ACLs. You can also assign granular access permissions for each of the containers. That is, you can use IAM to restrict access to each service and to configure which resources a container can access. And all these configurable isolation features enable you to use ECS to build highly secure and reliable applications. In terms of scale, you can use ECS to launch tens or tens of thousands of Docker containers in seconds with no additional complexity. It's important to understand that containers are instantiated as part of a task, and that these Amazon ECS tasks are defined through a task definition, which is a declarative JavaScript object notation or JSON template. You use the task definition to specify one or more containers that are generally related or working together in the context of the task, including the Docker repository and image, the memory and CPU requirements, any shared data volumes, and how the containers are linked to each other. With ECS, you can launch as many tasks as you want from a single task definition, but you must first register the task definition with ECS. Thanks for watching. See you in the next video.
Welcome. We will now review some of the most commonly used AWS database services. AWS offers a variety of fully managed database services to support the needs of different types of applications. AWS offers services for SQL and NoSQL databases. In the category of databases that use structured query language, also known as SQL, Amazon RDS and Amazon Redshift provide managed solutions for relational databases and data warehousing. Amazon RDS provides a choice of 6 popular database engines, and it is ideally suited for transactional applications. Amazon Redshift addresses the needs of data analytics by providing a fast, scalable, and cost-effective data warehousing solution. Amazon DynamoDB, Amazon Neptune, and Amazon ElastiCache offer database solutions for NoSQL applications. DynamoDB supports document, key value store models, and transactional workloads. Neptune is a graph database service that supports applications that manipulate highly connected data sets. Neptune provides continuous backup to Amazon S3. It also provides point-in-time recovery with replication across multiple availability zones. Amazon ElastiCache is an in-memory data cache solution that supports the open-source Redis and Memcached engines. This module focuses on RDS and Aurora. Aurora is an AWS database engine. We will also review DynamoDB, which is one of the more common choices among the AWS NoSQL database offerings. Earlier, you learned that AWS offers services for SQL and NoSQL databases. You will now learn about the difference between a SQL database and a NoSQL database. An SQL database conforms to the relational model, which stores data in rows and columns. Rows contain all the information about one entry, and columns are the attributes that separate the data points. An SQL database schema is fixed. Column definitions must be locked before data entry. If you want to change a database schema, you must take an SQL database offline. Data in SQL databases is queried by using the structured query language, which allows for complex queries. SQL databases scale vertically by increasing hardware power, such as RAM, CPU, and disk IOPS. NoSQL databases are non-relational. They store data by using one of many storage models, including key-value pairs, documents, or graphs. Originally, the term NoSQL referred to a non-SQL or non-relational database. However, NoSQL can also support SQL-based queries. NoSQL schemas are dynamic, and information can be added rapidly. The key difference between the two types of databases is that in a NoSQL database, a row does not need data for each column. Data in NoSQL databases is queried by focusing on collections of documents. NoSQL databases scale horizontally by increasing the number of servers. Think automatic scaling. Choosing the right database services requires a good understanding of the capabilities of the service and the needs of the application. For example, some database engines use the relational model and are well suited for transactional applications. Other database engines conform to the NoSQL model and are intended for internet scale applications. Others are ideal for real-time workloads that require an in-memory data store for caching. Therefore, it is important to consider and match the requirements of the application workload with the capabilities of the database service. Some key workload characteristics to consider include whether the data is highly structured, the size of the data set, and your computational requirements. Don't forget to consider the way you must access the data and your performance needs. Here are some general recommendations for when to use the different types of AWS database services. The key takeaway is that AWS offers a broad range of databases that are purpose-built for specific application use cases. These fully managed database services include relational databases for transactional applications and non-relational databases for internet scale applications. They also include a data warehouse for analytics, an in-memory data store for caching and real-time workloads, and a graph database for building applications with highly connected data. Spend time considering your application's purpose before deployment. Here are some of the more common use cases for the different AWS database services. Amazon RDS and Aurora are generally used for transactional database applications, like enterprise resource planning or customer relationship management systems. Amazon Redshift is a service you can use for analytical applications and when working with very large data sets. Amazon ElastiCache is typically used for real-time applications that require sub-millisecond latency. We're talking fast. Neptune is commonly used for highly connected data like news feeds or web applications that provide recommendations. DynamoDB is generally the database service to use for highly